Welcome to our deep dive into PyTorch RNNCells. Today we're going to explore the fundamental building blocks of recurrent neural networks. Let's look at our learning objectives. We'll understand the RNN cell architecture and computation, master all the parameters and their effects, learn to process sequences step by step, implement custom RNN layers using RNNCell, and apply RNNCell to practical problems. Now let's set up our environment. We're importing PyTorch and the Neural Network module, along with NumPy for numerical operations and Matplotlib with Seaborn for visualizations. We'll set a nice plotting style and initialize our random seed to 42 for reproducibility. Perfect, our environment is ready with the random seed set. Let's visualize the RNN cell architecture. The RNN cell is the fundamental building block of RNN layers. It processes one time step at a time, maintaining a hidden state that captures temporal information. Looking at this diagram, you can see how the cell takes an input at time t, combines it with the hidden state from time t-1, and produces a new hidden state. This hidden state carries forward the temporal context. Now let's understand the mathematical foundation. The RNN cell implements a specific computation. It calculates h at time t equals the activation function applied to WIH times xt plus BIH, plus WHH times h at t-1 plus BHH here. Xt is our input at time step t. H at t-1 is the hidden state from the previous time step. WIH and WHH are our weight matrices. BIH and BHH are our bias vectors, and the activation is either tanh or ReLU. Let's start with the simplest RNN cell example. Here we're creating a basic RNN cell with input size 10 and hidden size 20. We'll create a single input tensor and initialize our hidden state to zeros. Then we'll perform a forward pass through the cell. Notice how we pass both the input x and the previous hidden state h to get our new hidden state. Great, we can see the input has shape 1 by 10, the hidden state output has shape 1 by 20, and the output values range from -0.621 to 0.606. This confirms our output is bounded by the tanh activation function, which keeps values between -1 and +1. Let me show you the complete documentation of RNN cell parameters. We have input size, which is required and determines the weight IH dimensions. Hidden size is also required and determines the output dimension and all weight shapes. The bias parameter defaults to true and adds learnable offsets. The nonlinearity parameter defaults to tanh and controls the output range and gradient flow. We also have device and D-type parameters for placement and precision control. Now let's explore the weight matrices and biases in detail. We're examining the parameters of our RNN cell. We have four main parameters. Weight IH connects the input to hidden with shape 8 by 5. Weight HH connects hidden to hidden with shape 8 by 8, and we have two bias vectors, both of size 8. Notice how the weights are initialized uniformly within a specific bound, which is the square root of 1 over the hidden size. This initialization helps with training stability. Excellent, we can see all four parameters with their shapes, and they all require gradients for training. The initialization bound is plus or minus 0.3536, and our weight IH values fall perfectly within this range. Let's visualize these weight distributions to better understand the initialization. Looking at these histograms, we can see all weights are uniformly distributed within their bounds. The weight matrices show a nice uniform distribution, while the bias terms are also initialized within the same bounds. The red dashed lines show our initialization boundaries. Let's explore the effect of the bias parameter. We're comparing two RNN cells, one with bias and one without. We'll use the same input and hidden state for both and observe the differences in their outputs. This will help us understand how bias terms affect the computation. Interesting, with bias, we get an output mean of 0.0616 and standard deviation of 0.6369. Without bias, the mean is 0.0504, and standard deviation is 0.5199. As expected, the RNN cell with bias has the bias terms, while the one without bias has none for bias IH. Now let's compare the different nonlinearity options, tanh versus ReLU. We're creating two RNN cells with different activation functions. To make a fair comparison, we'll copy the same weights from the tanh cell to the ReLU cell. Then we'll process the same input through both and compare their outputs. Perfect comparison. The tanh output ranges from -0.968 to 0.98, staying within its bounds of -1 to +1. The ReLU output ranges from 0 to 2.297 with no negative values. We can see 48% of tanh outputs are negative, while ReLU has 0% negative values, which is exactly what we expect from these activation functions. Let's visualize these activation distributions to see the differences more clearly. Looking at these distributions, the tanh activation on the left shows outputs spread between -1 and +1 with values on both sides of 0. The ReLU activation on the right shows all positive values with a concentration at 0, representing the rectified linear behavior. Now let's understand sequential processing with RNNCell. The RNNCell processes sequences one time step at a time, maintaining hidden state across steps. Looking at this diagram, you can see how the hidden state flows from one time step to the next, carrying temporal information forward through the sequence. Let's implement sequence processing step by step. We'll create an RNN cell and process a sequence of length 8. We'll start with a 0 hidden state and update it at each time step. Watch how the hidden state evolves as we process each element of the sequence. Excellent, we've processed all 8 time steps. You can see how the hidden state statistics change at each step, with the mean fluctuating between -0.167 and 0.03, and the standard deviation ranging from 0.384 to 0.477. Our output sequence has the expected shape of 8 by 3 by 20. Let's visualize how the hidden state evolves over time. These visualizations show the hidden state evolution beautifully. On the left, we see the L2 norm of hidden states increasing over time for each batch. On the right, the heat map shows how individual hidden dimensions change across time steps, with warmer colors indicating positive values and cooler colors indicating negative values. Now let's verify the RNN cell computation manually. We'll manually compute what the RNN cell does internally. The computation is H equals tanh of WIH times X plus BIH, plus WHH times H previous plus BHH. We'll implement this formula directly and compare it with the RNN cell's output to verify they match. Perfect verification. Our manual computation matches the RNN cell output with a maximum difference of only 1.19 times 10 to the -7. Looking at the computation breakdown, the input contribution has a norm of 1.58, the hidden contribution is stronger at 3.16, and after applying tanh, the final output norm is 1.97, showing how the activation function bounds the values. Let's analyze gradient flow and backpropagation through the RNN cell. We'll track gradients through a sequence of 5 time steps. We'll compute a loss on the final output and backpropagate to see how gradients flow backward through time. This is crucial for understanding training dynamics in RNNs. Excellent gradient analysis. We can see the input gradient norm is 0.0488, weight IH gradient is 0.3275, and weight HH gradient is 0.2079. Notice how the gradient norms increase as we go back in time, from 0.0013 at step 0 to 0.0171 at step 4. This shows how gradients accumulate as they flow backward through the sequence. Let's visualize these gradient flow patterns. The visualization clearly shows the gradient flow pattern. On the left, we see gradients increasing toward later time steps, which makes sense since we computed loss on the final output. The heat map on the right shows gradient distribution across different batch samples and time steps. Now let's build a custom RNN layer using RNN cells. We're creating a custom RNN class that stacks multiple RNN cells to build a multi-layer RNN. Each layer processes the sequence and passes its output to the next layer. This gives us fine-grained control over the architecture. The forward method processes the input sequence through all layers, maintaining separate hidden states for each layer. Our custom RNN with 2 layers is working perfectly. The input shape is 6 by 3 by 10, the output shape is 6 by 3 by 20, and the final hidden state has shape 2 by 3 by 20, with one hidden state per layer. Let's look at a practical application, sequence generation. We're building a sequence generator using RNNCell. This model takes an initial input and generates a sequence autoregressively, meaning each output becomes the input for the next step. This is how many text generation and time series prediction models work. We'll generate 8 steps from our initial input. Perfect sequence generation. Starting from an initial input of shape 2 by 5, we've generated a sequence of shape 8 by 2 by 5. The final hidden state maintains the context of the entire generated sequence. Let's visualize the patterns in our generated sequence. These visualizations reveal interesting patterns in our generated sequence. The top left shows how different dimensions evolve over time. The heat map shows the generated values across all dimensions. The bottom left displays the mean and standard deviation over time, while the autocorrelation plot on the bottom right shows temporal dependencies in the generated sequence. Now for something advanced, let's implement bidirectional processing with RNN cells. We're creating a bidirectional RNN using 2 RNN cells, one for forward processing and one for backward. The forward cell processes the sequence from start to end, while the backward cell processes from end to start. We then concatenate both hidden states at each time step to get bidirectional context. This is particularly useful for tasks where future context is as important as past context. Excellent, our bidirectional RNN is working. The input shape is 5 by 2 by 8, and the output shape is 5 by 2 by 24. The output dimension is doubled because we concatenate forward and backward hidden states, giving us 12 plus 12 equals 24 dimensions. Let's explore common pitfalls and best practices. We're demonstrating 3 important best practices. First, always initialize your hidden state, either explicitly with zeros or by passing none. Second, apply gradient clipping when processing long sequences to prevent gradient explosion. Third, ensure all tensors are on the same device to avoid runtime errors. These practices will save you from common RNN training issues. All best practices demonstrated successfully. Hidden state initialization works both ways. We see a gradient norm of 0.3206 before clipping, which we then clip to a maximum of 1. And all tensors are properly placed on the CPU device. Let's compare the performance of tanh versus ReLU activations. We'll train 2 RNN cells, one with tanh and one with ReLU, on a simple sequence prediction task for 50 epochs. We'll track their losses to see which activation function leads to better convergence. This practical comparison will help you choose the right activation for your tasks. Training completed successfully. The tanh activation achieved a final loss of 1.028, while ReLU achieved 1.0496. In this case, tanh performed slightly better, though both converged reasonably well. Let's visualize the training curves to see the convergence patterns. The training curves show interesting dynamics. Both activations converge, but tanh in blue shows slightly smoother convergence and achieves a marginally better final loss. The ReLU curve in green has more fluctuations, but still reaches a good solution. The log scale helps us see the exponential decrease in loss during early training. Let's summarize the key takeaways from our RNN cell exploration. First, the RNN cell architecture processes one time step at a time while maintaining hidden state across steps. Second, we have fine control through parameters like bias and nonlinearity. Third, for sequence processing, we loop through time steps manually with the same weights used at all steps. For best practices, always initialize hidden states properly, apply gradient clipping for long sequences, ensure tensor device consistency, and choose tanh for bounded outputs or ReLU for potentially faster training. Common applications include building custom architectures, implementing bidirectional RNNs, and sequence generation tasks. That's all for our comprehensive exploration of PyTorch RNN cells. Thank you for learning with us today.